Hello, this is Dr. Jambitsky and welcome to my environmental science screencast. Today we are going to talk about the pH of our environment. Welcome back. So let's continue our discussion about the importance of pH for our environment. So this would be the exact spot in our discussion where we stopped in our previous screencast. So we were approaching this important topic of acids and bases. And we have already discussed a definition of an acid. So we remember that acids are chemicals that add hydrogen ions to the water. And so because we will have more hydrogen ions in the water, the pH will drop. And so the pH of acids is usually less than 7. There are many examples of acids in our environment, but in a nutshell, as I always add hydrogen ions H+ to the water, and this is what makes the pH to drop. Now, the second definition here on the screen is definition of bases, and bases would be just the opposite of the acids. So if our acids will add hydrogen ions to water, our bases will do the opposite. They are going to remove hydrogen ions from the water. Okay. So this is the main difference. So let's think about it. So bases are chemicals that remove hydrogen ions from the water, and in addition, they will also add hydroxide ions to the water. And remember that hydroxide ions are have opposite properties of hydrogen ions. So, because hydrogen ions H+ are being removed from the water and replaced with hydroxide ions, or H-, that will make the pH to become more alkaline. The pH will climb up, so the pH will increase, and as a rule, our bases will have pH which is greater than 7. So let's think about it and let's look at some examples. So in a nutshell, once again, acids will add hydrogen ions to the water, right? And bases will do the opposite, and they are going to remove hydrogen ions from the water and add hydroxide ions. So the pH of acids is is less than 7. The pH of acids is less than 7, and the pH of bases is greater than 7. So very well. So it seems to be very simple and elegant. So let's take a look at some examples of acids and bases in our environment. So over here in red color, I have shown you one example of an acid. This is actually quite strong acid, which is called hydrochloric acid. So the molecular formula of hydrochloric acid is HCl. It means that the molecule of hydrochloric acid is made of one atom of hydrogen and one atom of chlorine. Now, so if I have hydrochloric acid and I'm going to dissolve hydrochloric acid in water, it will dissociate. You remember dissociation, this is a process when the molecule would break into ions, and the result would be hydrogen ions, H+, and chloride ions, Cl-. So what's going to happen in this case when hydrochloric acid is dissolved in water? I will have more hydrogen ions. My hydrochloric acid literally is going to add more hydrogen ions to the water. If we have more hydrogens in the water, that means that the pH will go down. So hydrochloric acid will make pH to be less than 7, and you can see that hydrochloric acid complies with this definition of acids because it is a chemical that adds hydrogen ions to water and decreases pH. So this is our hydrochloric acid. Now, let's take a look at the example of a base, which is shown here in blue color. So the chemical which is a good example of a base would be sodium hydroxide. And the molecular formula of sodium hydroxide is sodium OH. So this molecule is made of sodium atom, one sodium atom, one oxygen atom, and one hydrogen atom. Now, when I dissolve sodium hydroxide in water, what will I get? Well, I will get this. So sodium hydroxide in water will dissociate and will produce two types of ions, sodium ions, Na+, and hydroxide ions, OH-, right? So, as you can see here, my sodium hydroxide will add hydroxide ions to water, right? And the more hydroxide ions in water I will have, the higher will be the pH. In addition, what's going to happen with those hydroxide ions, as shown over here, they are going to join with hydrogen ions to reform water molecule. And because pretty much those hydrogen ions are being used up, the concentration of hydrogen ions will also decline. So we will have two things happening when we dissolve sodium hydroxide in water. Number one, we will have more hydroxide ions. Number two, we will have less hydrogen ions. And actually, this is a good example of a base, because if you look at the definition of the base, it's very clearly indicated here that bases are chemicals that remove hydrogen ions from water and add hydroxide ions. And this is exactly what happens here in case of sodium hydroxide. Obviously, the pH will climb up. It's going to be greater than 7. Alright, so these are two good examples of acids and bases. Very strong acid, hydrochloric acid, that adds hydrogen ions to water and drops the pH, and a very strong base, sodium hydroxide, that will add hydroxide ions to water and remove hydrogen ions. So this is a very serious and strong base. So if we have to handle a chemical which is a strong acid or a strong base, for example, in a laboratory, so we have to follow very serious precaution because those chemicals are very reactive, and if, for example, you spill them on your skin, you can have a very serious chemical burn. So because both hydrochloric acid and sodium hydroxide, if they're very concentrated, they're very reactive. They're very strong acids in case of hydrochloric acid, or bases in case of sodium hydroxide. So let's continue. So this slide introduces us to an idea of buffers. The definition of buffers is over here. So let's take a look. So as you can see, buffers are chemicals that can either add or remove hydrogen ions from water to resist pH change, right? So let's think about it. So these are very special chemicals that can either add hydrogen ions or remove hydrogen ions. So they can go both ways, and this will help to resist pH change. So how you can think about it? So imagine that pH becomes too acidic. So if pH is too acidic, what does it mean? It means that we have too many hydrogen ions. So what the buffer can do, it can remove the excess of hydrogen ions from water, and that would make the water less acidic. Now, if you have an opposite scenario, let's see the water is too alkaline. So that means that there isn't enough hydrogen ions, right? So in this particular case, a buffer can add hydrogen ions to water, okay? This will prevent pH from climbing up. So, in a nutshell, buffers will regulate pH and will prevent pH from changing. So, we have different types of chemicals in our environment that act as buffers. And so, here is an example. So, an alkaline rock can buffer acid precipitations. So you probably heard an expression acid rain. Unfortunately, due to air pollution, the acid rain is very frequent phenomenon. And so if I collect the rainwater and measure pH, it will be pretty acidic, right? So in our environment, there are chemicals that can fight this acidity, such as, for example, alkaline rock. The ocean by itself acts as a buffer system, and the ocean pH, which is approximately 8, is an alkaline pH. And if we have acid precipitation, acid rain, so the ocean water can act as a buffer to prevent or to resist the pH change. So what we have to keep in mind, however, that these buffer systems, such as alkaline rock or the ocean water, have only so much resilience, so to speak. And it's very easy to deplete the ability to resist pH changes if we put too much pollutants in our environment. So we can overwhelm the natural buffer systems, and they will not be able to resist the pH change any longer. And I would like to focus on another important idea which is shown here on this line about the rainwater. So let me explain what I mean here. So we already know that pH of pure water is 7, right? So, but what is pure water? Pure water would be, for example, the distilled water. And so the distilled water is purified by special process called distillation to remove all the impurities, right? So if I have distilled water, it's pure water, the pH will be 7. However, if I'm going to collect water from the water tap in my house, for example, I'm using public water system, is the pH gonna be 7? And the answer is not. It will be less than 7. Why? Because water that comes from the water tap is not pure water. So the water has been treated with certain chemicals before it was delivered to my house. So, for example, to disinfect it, to kill bacteria. So, for example, most townships will treat water with chlorine to kill bacteria. And so, because we have some chemicals added to water, the pH is not going to be 7. It's going to be less than 7. Now, so if I'm going to collect the rainwater, and this is what we are discussing here on the screen, and we assume that this is pure water that has not been polluted. So normal unpolluted rainwater has a pH of 5.6, right? So let's think about this pH 5.6. And I wanted to take you to this diagram, all right? So the pH of normal rainwater is 5.6. On this particular diagram is shown around 5, right? So it's pretty much similar to pH, for example, of coffee, right? And basically, the water that we collect in our house to prepare coffee probably also will have pH of 5, or maybe somewhere in the range between 5 and 6. Now, if we talk about the water that we collect from the water tap, right, we can guess why the pH is less than 7, because we add chemicals to the water. Now, if we collect rainwater, presumably nobody added chemicals there, right? So we are talking about pure unpolluted rain. So why is it that pH of rainwater is 5.6? So this is the first question that we would like to ask. So the pH of rainwater of 5.6 is considered to be pretty normal. And the question is why it is 5.6. But sometimes the pH of rainwater can drop below 5.6. And in this case, we say this is acid rain. So the pH of rainwater is 5.6 and more. So basically between 5.6 and 7, this is normal unpolluted rain. Pollution can drop the pH of rainwater below 5.6. So let's talk about this. So to understand what's going on with the rainwater, we have to kind of look at the composition of the air, or composition of the atmosphere. So this diagram from your textbook actually shows some molecules that could be found in the air. And some of those molecules are pretty obviously normal ingredients of clean air. And for example, if you are looking over here, you're recognizing nitrogen gas, right? And so nitrogen gas, as you already know, is a normal ingredient of the air that surrounds us. And you also know that nitrogen gas represents approximately 78% of the air composition. So another major ingredient that is a normal ingredient of the air is oxygen, O2, which is shown over here. And we also know that the normal composition of oxygen is approximately 21%. 21%. So this is how much oxygen do we have. Most of the air is nitrogen. Oxygen is 21%. We will also have water vapor, and water can be present in the air, and the quantity will depend on the relative humidity. So if we looking at the humid day, we will have more water vapor in the air. If we are looking at more dry day, we will have less water vapor in the air. However, it will be still present. We always have water vapor in the air. Now, if we are looking at the dry air or a regular air, carbon dioxide is also a very common ingredient that we will find in the air. And the concentration of carbon dioxide is approximately 0.4%, right? And if you remember the table of the normal composition of air, it's actually approximately 0.035%, right? But if you round it up, it's going to be approximately 0.4. And again, carbon dioxide is a normal ingredient of the air together with nitrogen, oxygen, water vapor. So every living creature, or almost every living creature, exhales carbon dioxide, right? So for example, humans and animals exhale carbon dioxide. So it's a normal ingredient of the air. In nature, as we remember the writings of George Perkins Marsh, everything is balanced, right? And fortunately, there is a process of photosynthesis that we have already discussed before during this class. And in the process of photosynthesis, green plants can capture carbon dioxide. So in nature, there is this fine balance. Animals exhale carbon dioxide, humans exhale carbon dioxide, plants in the process of photosynthesis take the carbon dioxide out of the air. And because of this balance, we should have the same concentration of carbon dioxide in the air all the time, right? It's a normal ingredient. By the way, carbon dioxide by law is also not considered to be an air pollutant because everybody exhales carbon dioxide. So carbon dioxide, it's not regulated by law. Now, there is another important process that liberates additional percentage of carbon dioxide. It's burning of fossil fuels. So humans are using fossil fuels such as oil, such as coal, such as natural gas. And in the process of burning of fossil fuels, we are adding extra carbon dioxide in the air. A lot more than we exhale, and a lot more than the process of photosynthesis can handle. And as George Perkins Marsh wrote in Man and Nature, humans disturb the fine balance of nature. And due to burning of fossil fuels, when we are driving cars, when we have industries that burn coal, etc., when we use fossil fuels for electricity production, we are actually putting additional carbon dioxide in the atmosphere. This can be a problem, and there are actually two main issues which are associated with carbon dioxide. And so the first issue is a greenhouse effect, because carbon dioxide is a powerful greenhouse gas. So let me write it down. So the first issue is greenhouse effect. So let's talk about it. Why carbon dioxide is a greenhouse gas? Well, when we have sun energy that delivers warmth to the planet. The sun warms, actually the sun rays warm up the surface of the planet first. The air is going to be heated from the surface of the planet, right? And in our air, we have different molecules. So we have nitrogen molecules, we have oxygen molecules, we have water vapor molecules, we have CO2 molecules, right? And CO2 molecules actually can trap the heat in the atmosphere. And this actually is very important because it keeps the Earth's temperature at a certain level. So if we're looking at other planets, such as, for example, Mars, they also have atmosphere, but they might have, different concentration of CO2. And depending on the concentration of CO2 in the atmosphere, there will be different heat amount that can be trapped. All right, so we know that carbon dioxide is a greenhouse gas because it actually traps the heat in the atmosphere of the planet Earth. And let's also talk about other planets that also have atmosphere, but the atmosphere of those planets might have different concentration of carbon dioxide. So, for example, we mentioned this planet, right? And the average temperature of the planet is approximately 80 degrees Fahrenheit. Okay, is approximately 80 degrees Fahrenheit. So this is pretty cold, right? Which is the same as negative 60 degrees Celsius. And you remember that the freezing point of water is at the Celsius scale is 0, right? So it's the average temperature on the surface of Mars is below the freezing point of water. And this is because the atmosphere of Mars has very, very little CO2. Very little CO2. There is nothing to trap the heat from the sun. Now let's take a look at a different planet in the solar system. So it's also kind of quite interesting. And this is a very hot planet. So the average temperature of Venus is 864 degrees Fahrenheit. Which is very, very hot. So if we are going to translate it into Celsius, is 462 degrees Celsius. Right, and again, this is several times higher than the boiling point of water. And Venus is so hot because the atmosphere of Venus is very rich in CO2. It has a lot more CO2 in the atmosphere compared to the planet Earth. Now, on planet Earth, remember, we had approximately 0.4% of our carbon dioxide. So the presence of carbon dioxide is kind of important to maintain the correct temperature on the planet. This is a greenhouse gas. However, due to various activities that involve burning fossil fuels, that concentration of carbon dioxide in the atmosphere can actually increase and trap more heat and increase the global temperature, which is called the global warming. So here we go. This is our first problem associated with increase of carbon dioxide is a greenhouse effect. Greenhouse effect. So since we are talking about the greenhouse effect, so let me also mention a different molecule which is a very powerful greenhouse molecule in addition to carbon dioxide. This molecule is not a normal ingredient of the atmosphere. It's more of a pollutant. It's methane, CH4, which is over here. So methane is a powerful greenhouse gas. So it is even stronger than CO2. It is more powerful greenhouse gas. So another very powerful greenhouse gas is water when it is in form of water vapor. Okay, so now let's talk about water. So imagine that we have global temperature rising, and so if the global temperature is higher, that will result in more evaporation of water from the surface of the ocean, right? And water vapor is a powerful greenhouse gas by itself. So burning more fossil fuels will release more carbon dioxide. Carbon dioxide traps more heat in the atmosphere, leading to the increase of global temperature. Increase of global temperature will result in more water evaporation from the surface of the oceans and lakes and rivers, and water vapor makes the greenhouse effect even stronger. So this is like a vicious cycle. One thing leads to another, right? Now, what about methane? So let's talk about methane and how methane can contribute to greenhouse effect as well. So methane is natural gas, right? Or one of the natural gases, similar to propane. So the structure of the propane is a little bit different. Instead of one carbon, propane has 2 carbons, but methane is similar to propane. You might be familiar with propane. You might buy it at Home Depot to use it with your grill in your backyard, the propane tank. So methane is just like this. So some of the methane can escape to the atmosphere during the process of natural gas extraction or oil extraction. And in this case, it will be a pollutant that will increase the greenhouse effect and will result in more pronounced increase of global temperature. Now, let me tell you about another source of methane. So methane, CH4, is also produced as a process of agricultural production of beef. So cows are vegetarians, right? And they chew grass or hay or corn or any other type of plant material all day long. And it's quite difficult to digest grass or hay or other type of food that cows are eating. So in the stomach of cows, we have special bacteria that are helping them to digest grass or hay or corn or any type of cow feed, right? And when those bacteria in the stomach help to digest the food, they produce methane, CH4, as a byproduct. And periodically, a cow would burp the methane out, right? And this is not a big deal if you have a cow here and there on a small farm, but we are producing beef in industrial quantities. So there's like thousands and thousands and thousands of animals crammed in those industrial farms, and they produce a lot of methane. And remember, methane contributes to the greenhouse effect. And that's why environmentalists very frequently say that if we change our habits, if we change our diet, that can help to slow the greenhouse effect, right? So if we switch to a different type of meat, for example, from beef to chicken or to the vegetarian diet, we will not be, raising cows to be slaughtered for food, and there will be less methane produced and liberated in the atmosphere. So this is how our diet can help if we change it to combat global warming. All right, so we have discussed several molecules here that can contribute to global warming and greenhouse gases. That's going to be CO2, carbon dioxide, that's going to be water vapor, and methane over here. So all three are powerful greenhouse gas molecules. But remember, when we were talking about CO2, I said there are two main problems associated with increase of CO2 in the air. And the first problem that I mentioned was the greenhouse effect, right? But if there are two problems, and one of them is a greenhouse effect, so what is the second problem? So the second problem is acidification of the environment. Acidification of the environment. This is our second serious problem associated with burning fossil fuels and liberation of CO2. So CO2 makes our environment more acidic. What exactly does this mean? So let's talk about acidification of the environment due to human activity. And we are going to start with CO2, carbon dioxide. So let's say we are burning fossil fuels, right, such as natural gas, coal, and oil. So for example, we are driving a car and CO2 comes out of the tailpipe of our car. And so it gets to the air, right? But eventually, CO2 is gonna dissolve in water. For example, it will dissolve in the ocean water or river water or lake water, etc., etc. And it's important to remember that when our CO2 dissolves in water, it actually produces carbonic acid, right? The formula of carbonic acid is H2CO3. So this molecule is made of 2 hydrogen atoms, 1 carbon atom, and 3 oxygen atoms. And so what's going to happen if, for example, CO2 will dissolve in ocean water, right? And carbonic acid is produced, the pH of ocean water will drop. So normally it's around, the pH of ocean water is around 8, so it will become less than 8. It becomes more acidic because of carbonic acid. And we know that ocean water by itself is a buffer. It has resilience and it has ability to resist the pH change, but unfortunately we are burning so much fossil fuels that the amount of carbonic acid that we put in the ocean is overwhelming, and the ocean as a buffer cannot handle this anymore. You know what? Our CO2 is not the only molecule that contributes to acidification of the environment. There are more. And so let's go back to our original slide. So far, we only discussed molecules which are normal ingredients of the atmosphere. And that was our nitrogen, our oxygen, our water vapor, and our carbon dioxide. We also mentioned that human activity can increase the concentration of carbon dioxide and produce greenhouse effect and also make our environment more acidic. We talk about methane, that is another example of greenhouse gas, which is an air pollutant. And there are two other molecules on this slide here, which are air pollutants. This is sulfur dioxide, SO2, which is made of one atom of sulfur and two atoms of oxygen, and nitrogen dioxide, NO2. This molecule is made of one nitrogen and two oxygen atoms. So these are not normal ingredients of the air. Very small quantity of SO2 and NO2 can be liberated to the atmosphere during volcanic eruption. However, it's very minuscule quantity. Human activities produce SO2 and NO2 as air pollutants, and both of these pollutants make our environment extremely acidic. So let's see how does it work. Let's take a look at sulfur dioxide first, which is here in the middle of the screen. So SO2 is sulfur dioxide, and it's important to remember that when SO2 is dissolved in water, it actually produces sulfuric acid. So the sulfuric acid formula is H2SO4. So it is made of 2 hydrogen atoms, 1 sulfur atom, and 4 oxygen atoms. And sulfuric acid is very, very strong, right? And makes our environment very acidic. So when sulfur dioxide dissolves in water, it produces the sulfuric acid, which makes our environment acidic. Okay, now let's take a look at nitrogen oxide. And as a matter of fact, humans produce two types of nitrogen oxide that have similar effect on our environment. So let's take a look at them. So the first molecule, we are familiar with this molecule already, is NO2. This is nitrogen dioxide, right? Di means two. So the second molecule is similar, but it only has one oxygen, NO, and this is nitrogen monoxide. Mono means one. So nitrogen oxide can have two oxygens, such as in case of NO2, or just one oxygen, such as in case of NO. So both nitrogen dioxide, NO2, and nitrogen monoxide, NO, together can be written like this, NOx. When X indicates the number of oxygen atoms, which can be either 2 or 1, right? NOx, sometimes we say NOx. So when both these oxides, or we can say NOx, is dissolved in water, it will produce nitric acid. Nitric acid formula is over here, HNO3. It is made of 1 hydrogen, 1 nitrogen atom, and 3 oxygen atoms. And nitric acid is also extremely strong acid that makes our environment very acidic. All right, so nitrogen oxides, NOx, when dissolved in water, produce nitric acid. So these are three chemicals that actually make our environment more acidic or cause acidification of the environment. CO2, which is carbon dioxide, SO2, which is sulfur dioxide, and NOx, which includes nitrogen dioxide and nitrogen monoxide. So the next question would be, where do they come from, those gases? So we already know that CO2 comes from burning fossil fuels. So what about SO2 and NOx? So this is a pie chart from your textbook where we are talking about the air pollution. And CO2 is not considered by law to be an air pollutant. However, both sulfur dioxide and nitrogen oxide are considered to be air pollutants by law. And in the United States, we have very important environmental law that protects the quality of our air, which is called the Clean Air Act. All right, and the government can use this law to regulate the air pollutants. And both nitrogen oxides and also sulfur dioxide will be regulated according to the Clean Air Act. So let's take a look at the sources of our nitrogen oxide and sulfur dioxide. So let's start from sulfur dioxide, which is shown over here. So this is a pie chart, and we also already had the activity that taught you how to read the pie chart and how to construct a pie chart. And so this particular pie chart shows us the main sources of sulfur dioxide as a pollutant. And you can see that most of it comes from power plants. What kind of power plants? This is going to be primarily coal-burning power plants. So if you have a coal-burning power plant that produces electricity, it burns coal. And so when we burn coal, the air pollutants, including sulfur dioxide, are going to travel to the air. And eventually, this sulfur dioxide is going to mix with water and produce sulfuric acid that can precipitate on our head as an acid rain. Other industries, such as, for example, smelting, will also liberate additional quantity of sulfur dioxide. So let's take a look now at the sources of nitrogen oxide, NO and NO2, which are also very powerful oxides in terms of acidification of our environment. So if we are going to analyze this particular pie chart, we will see that approximately 1/3 of nitrogen oxides will come from the power plants as well. And that would be coal-burning power plants, mostly. So another third of nitrogen oxides come from transportation. So when we are driving our car, what comes out of the tailpipe besides CO2? Nitrogen oxides, NOx. So if you are going to the state inspection every 2 years, a technician at the inspection station is going to hook a special device to your tailpipe, and what they're measuring those pollutants which are regulated by the Clean Air Act, including nitrogen oxides. So, and not only transportation in form of private cars, but also commercial transportation can contribute to nitrogen oxide pollution, such as airliners and commercial trucking, etc., etc. So now we know where nitrogen oxides come from. Again, when they mix with water, they form nitric acid, which is quite powerful chemicals that make our environment very acidic. Let's take a look at this map. So remember the pH of 5.6 for the rain, it's pretty obviously normal, right? 5.6, so somewhere between 5.6 and 7. And this is because we normally have approximately 0.4% of CO2 in the air, and it will dissolve in water and produce carbonic acid. However, acidity of 5.6 is probably well tolerated by the environment, so we have different buffers, such as, for example, alkaline rock. The ocean water acts as a buffer. However, if the pH of water drops below 5.6, this is a problem, and our buffer system will be overwhelmed. And what this map shows us is an average pH of rainwater in different parts of the United States. And here we have a color code that shows us that probably more or less normal pH, which is more than 5.3, is green, and extremely acidic pH, which is less than 4.3, definitely acid rain, is bright orange. And so let's take a look at the area where you and I live. So here's the state of New Jersey. So if we are going to zoom in, we will see that in the state of New Jersey, we have two shades of orange, right? The rainwater is more acidic in the northern New Jersey. In the southern New Jersey, it's a little bit less acidic in the central Jersey. So if you are thinking about the pH of rainwater in New Jersey, so it is definitely in the acidic range here, right? So if we are going to look at the color code over here, so I would say that it's somewhere around 4.4, 4.3, 4.4. It's extremely acidic. So generally, you can also see that the East Coast will have lower pH of the rainwater, more acidity compared to the Midwest and the West Coast. So what does it tell us? In the state of New Jersey, the rain is quite acidic, and next time you go outside, make sure you carry an umbrella, because you don't want this acid to be on your head, right? So we can start thinking, why do we have this discrepancy in acid precipitations? And first of all, think about how densely this area is populated, how much industry do we have here, and how much different pollutants and CO2 is going in the air here. Think about how densely populated is the small state of New Jersey is. How many cars do we have per square mile of our territory? How many people do we have here? So we have more people, we need more electricity, so we have to burn more coal to produce more electricity, etc., etc. And this will be true probably for this area where we have, for example, a lot of industry, such as Detroit, for example, where we have factories manufacturing cars in the Great Lake area, etc., etc. Also, if you compare the density of population in New Jersey, like to the density of population like of Nebraska, there will be, a big difference, right? Obviously, there's a lot of people in the small New Jersey compared to the larger state of Nebraska, where there will be less people per square mile. Now, another thing, just think about the historical trend, how the continent was explored, right? So exploration started from the East Coast and then migrated to the West Coast. Pretty much probably on the East Coast, we also have all the technologies and all the factories and all the power plants, etc., which probably produce more pollutants compared to more contemporary power plants that we might have over here, right? So here we go. This is something to think about the acidity of the rain in the United States. So acidification of the environment may have very detrimental effect to different type of ecosystems and to the ecosystems of the ocean, obviously, because the pH of ocean water, drops and becomes more acidic. There are multiple type of organisms that are suffering from acidification of the ocean. For example, coral reefs. So coral reefs are very beautiful, and corals can be of different colors. So we have gold coral, and we have brown coral, and we have red coral, and blue coral, and gold coral, all kinds of colors. Corals also come in variety of different shapes. Sometimes they resemble fans, sometimes they resemble trees, sometimes they resemble structures like this. This is like a brain coral because it does look like a brain. And unfortunately, at the current time, we lost approximately 50% of our corals. They are dying for two reasons: because the ocean water becomes more acidic and the water temperature is rising due to global warming. So very frequently, these two factors cause coral reef bleaching. So let's talk about coral reef bleaching. And what is coral? So is coral alive? And the answer is yes. Is it a plant or is it an animal? And sometimes, because corals are sedentary, they're not moving, some students say that corals are plants. However, corals are not plants. Corals are animals. So corals are tiny animals that are called coral polyps. Okay, so here's the name, coral polyps over here. So they live as a colony. They live together, and they build like a shell around the colony. And the shell is made of calcium carbonate, which is another way to say limestone, right? And these organisms, coral polyps, actually, maybe you know that, they are close relatives of jellyfish, with exception that jellyfish is floating and the coral polyps are attached and they live as a colony. And coral polyps form a beneficial relationship with other type of organisms which are called algae. So the type of relationship when we have two or more species that are very connected to one another is called symbiosis. And if the relationship between two organisms is mutually beneficial, this relationship is called mutualism. So coral polyps form a mutually beneficial relationship or mutualism symbiosis with algae. Algae actually live in the tissue of the corals, and they give corals the color, the gold or the red, etc. Those tiny microscopic algae that live in the tissue of coral polyps. So why this is a mutually beneficial relationship? Mutualism. Well, it's good for the algae because the coral polyp colony is their home, so to speak. Algae are capable of photosynthesis, and they can produce food in the process of photosynthesis that coral polyps can use, right? That's why this relationship is mutually beneficial for both coral polyps and algae. Now, what's going to happen if the ocean pH becomes more acidic, so we have acidification, and the temperature is higher because of global warming? So those algae that form symbiosis with corals actually can die, and then the coral can lose color, and this is what we call coral bleaching. So acidification of the ocean water and temperature increase cause coral reef bleaching. So when the coral is bleached, it doesn't mean that it is already dead, but it means that the coral is extremely stressed. And if those algae do not recolonize the coral will eventually die. And this is what happening at this time. The corals are gradually dying off. And unless we prevent pH of ocean becoming even more acidic and the water temperature becoming even warmer, we may eventually lose all the corals on the planet. So this is an example of a coral reef bleaching. So this is a coral of a normal color. So that looks like this is like a goldish brownish coral. And the same coral that has been bleached. So it's turning snow white. So it's losing its color and it's probably gonna die eventually. So it's very sad because coral reefs are very, very complex ecosystems. Very frequently we call them the rainforests of the ocean because there are so many different organisms that form mutually beneficial relationship with corals, including turtles, marine turtles, including certain species of shark, sea anemone, clownfish, and many other interesting and unique species that are dependent on the coral. So not only a coral reef bleaching will lead to extinction of corals, but also it will damage other species which are very tightly interconnected with the coral reefs. It's very, very sad to see that, coral reefs are probably will have to go eventually. There are other forms of marine life that will suffer from acidification of the ocean. Usually these are younger forms of life such as fish, eggs, and larvae. And the ocean, gradually will change if we don't do something. And, there will be always some type of life in the ocean. It will evolve. But is it the life that we want to see in the ocean? So we have coral reefs and we have beautiful species of fish and turtles and other organisms. Well, maybe eventually there will be some form of life in the ocean, but maybe it's only going to be slime and ooze, right? It might be not necessarily what we want. So we have to do something to protect our oceans. So I hope you can appreciate how important to understand what pH is and how pH of our environment is changing due to human activity. So if you have questions, I will be looking for your questions. You know how to get in touch with me. And otherwise, I will talk to you soon. After my presentation, I would like to show you a brief video about coral reefs that have some other interesting examples of mutually beneficial relationships between corals and other species. So here we go. Enjoy the video.
From above, the ocean looks empty. Like a desert made of water, it seems barren, uninhabited. But that's just on the surface. Come below the waves with me as we explore the riot of color and life that exists on the coral reefs. Coral reefs are only found in shallow tropical seas. They may look like colorful rocks or even plants, but coral is really an animal. Coral is built by polyps. Polyps are very small creatures that are related to jellyfish. Unlike the jellyfish, which propel themselves around through the water, coral are stationary. They grow together in a colony called a coral head. A small piece of coral may be made of hundreds of polyps, A bigger one may have thousands. Hard corals create the reef by secreting calcium carbonate, or limestone, a type of rock, which gradually builds up into a solid structure. Coral grows slowly, only a few centimeters a year. It can take hundreds of years to form large pieces like this. Of course, not all coral is hard. Some types are soft. They may look like fans, bushes, or feathers, but once again, it is really a colony of tiny animals living together. When many corals grow close together, it's called a reef. Reefs provide very important habitat for fish and other sea creatures. Coral provides shelter for little fish, a place to hide. That many small fish in one place attracts big fish, which in turn attracts big predators, like sharks. This nurse shark is unusually active for the daytime. Usually, a nurse shark will hide under ledges or in crevices of the reef and come out at night to eat dormant fish that are hiding in the coral. Nurse sharks are slow-moving bottom dwellers and, for the most part, harmless to humans, although they can grow up to 14 feet, more than 4 meters in length. Their strong jaws allow them to crush shellfish and even coral if need be, but they prefer to eat shrimp, fish, and squid. The reef also provides a place for algae and sponges to grow. This provides food for a variety of creatures. For example, the sea turtle. The hawksbill sea turtle, like most other kinds of sea turtles, is endangered. Hunted for their meat and for their shells, trapped in commercial fishing nets to drown, and sickened by pollution, their populations are declining. These turtles rely on the food that grows on the coral reef, and the reef, in turn, relies on the turtles. It's a partnership that benefits both creatures. The turtles get a reliable source of food. The reef system gets a less obvious advantage. Without the turtles coming to eat the algae and sponges, they would overgrow the reef, preventing the coral from growing and expanding. With lowered turtle populations in oceans worldwide, the health of coral reef systems will suffer. It is important for people to do our best to protect these peaceful reptiles, not just for their sakes, but for the health of the entire coral ecosystem. Turtles and coral aren't the only partners you can find on the reef. Sea anemones are another animal that seems more like a plant. A relative of both coral polyps and jellyfish, anemones have their own partner to help make life easier: clownfish. Although it may not look like it, anemones are predators. They have stinging cells in their tentacles that allows them to paralyze their prey, usually small fish or shrimp, and then move them towards their mouth. Clownfish escape the anemone's sting by covering themselves in a protective layer of mucus. By hiding inside the anemone, clownfish are protected from predators that don't want to be hurt by the anemone. But what does the anemone get out of this, you may ask? Well, the little clownfish can chase away butterfly fish that would eat the anemone, and they can also clean the anemone of parasites and bits of food that the anemone has no way of cleaning itself. There's one more unusual pairing we're going to talk about today: Can you guess what parrotfish and beaches have to do with each other? Parrotfish are a distinctive family of fish species with a tough, bony beak so strong that they can bite through rock and coral. They do this so that they can eat the coral polyps and algae inside. The coral is ground up, and all of the edible parts are digested until only the limestone remains. Then the parrotfish has to get rid of all the crushed limestone, and there's only one way to do that. The parrotfish will excrete or poop out the limestone, which has been crushed into a fine sand. In this way, a single parrotfish can produce 200 pounds or 90 kilos of sand every year. You heard that right. The next time you bury your toes in soft white sand at the beach, just remember, you're making castles with fish poop. Coral reefs are sometimes called the rainforests of the sea. Though they cover only a tiny area of the ocean, they provide a habitat for a quarter of ocean animals. Unfortunately, the coral reef ecosystem is a fragile one. The delicate balance between the coral, algae, fish, and animals that live there is easily disrupted. Overfishing by humans, ocean pollution, and warming temperatures have all put the world's coral reefs at risk. Right now, more than half of the world's reef systems are in danger of destruction, and if nothing changes, then within 15 years, nearly all the coral in the world will be in danger of dying and disappearing. Fortunately, there are some simple things you can do to help protect coral reefs. Be careful not to waste water or pour chemicals down your drain, since eventually the water you use will reach the ocean and can increase pollution. Pick up trash that you see on the ground and recycle what you can so that garbage won't find its way into the water. Most importantly, make sure people know that you want to protect the coral reefs, so that when we make decisions about how to take care of our world, we will make choices that will protect the reefs. I hope you learned something new exploring the reef with me today. Goodbye till next time.